Hi, I'm Marcus Kalander from Huawei's Noah's Ark Lab, and I'm presenting our work, an influence-based approach for root cause alarm discovery in telecom networks. This is a joint work with Keli Zhang, Zhou, Zhang, and Junjian. So let's start a bit with a short introduction to the problem that we want to solve. We consider telecommunication networks, which can have thousands of interconnected devices that work together to service the users. The network topology can be seen as an hierarchical graph. In these types of networks, alarms are used to signal if there's been an anomaly or network failure. And when a failure actually occurs in the network, an operator will analyze all the relevant alarm and network information. However, there is actually too much information available. So these types of network can generate millions of alarms in a single day, often with hundreds of different alarm types, depending on the information conveyed. And these alarms can actually propagate throughout the network, depending on the network topology and the alarm types. So a single network fault can trigger a flood of alarms from multiple connected devices. So what we want to do is to determine the most significant alarms for fault management. And in reality, not all alarms are relevant for this task. So for each specific failure, there exists a subset of the most significant alarms among all the alarms that occurred in relation to the failure. And we denote these alarms as the root cause alarms. And in this work, our main goal is to identify these. So this is the overall system architecture of our framework. And since it's hard and very time consuming to get good labels for this problem, and there can be large differences between different networks, so we have kept our approach to fully unsupervised. And there are two main procedures, one online at the top of the figure and one offline at the bottom, with pre-processing shared between the two. And in the offline procedure, we use the historical alarms to construct an alarm influence graph. The graph is then used in the online process on the real-time alarm stream to rank the incoming alarms. We then consider the top K alarms as our root cause alarm predictions. To start with, I will briefly present the pre-processing step and then go into more details about the influence graph construction and the influence ranking. So in the table at the top of the slide, an example of the raw alarm data can be seen. And for our purposes, the alarm name or alarm type, the source node, and the occurrence times are the most relevant ones. For the first pre-processing step done is to remove any alarms that are known to be redundant. And so, for example, there are some alarms that are purely informational, and there are some periodical alarms that repeat with a set frequency, and these are not interesting in the perspective of fault management. Also, any alarms with incomplete information are also removed. Then the next step is to aggregate the alarms together. So devices in connected subgraphs in the network can interact with each other. This is known. That also means that alarms from these devices can potentially be related to the same network failure. So we therefore aggregate alarms in these same connected subgraphs together. Furthermore, the time is also a very important factor here. So alarms related to the same failure will generally occur together within a short time interval. So we further aggregate alarms by a time window W. And this, for the window size, it can be adjusted depending on the network characteristics. And in our case, on our data, we set this to 5 minutes. Then after the aggregation, we denote each group as an alarm sequence. For each aggregated group, we only keep the information of the alarm types and their occurrence times. We also further transform the alarm sequences into alarm transactions. For the alarm transactions, we only keep one element for each alarm type in the window, together with the first occurrence time and the number of alarms of this type. So these are two slightly different representations of the same underlying information. So after the alarm pre-processing, we want to construct the alarm influence graph. This is a graph with the alarm types as nodes and their relations as the edges. And this graph is constructed in two steps. First, we infer the initial causal structure by using a hybrid causal method, structural learning method, HPCI. Then we infer edge weights using a network embedding method, CPBE. For the first step, we use a multidimensional HAWKS process. This is a very popular tool to model continuous time event sequences where the past events can excite the probability of future events. And the key part is the conditional intensity function, which indicates the occurrence rates of future event conditioned on past events. So that's the lambda function in the slide here. For the alarm type U, we have a background intensity mu and the kernel function k, which indicates the influence of past events from all alarm types V on the current alarm type U. Here we use an exponential kernel function where we have a decay with time. So the longer time that passes since an alarm, the less influence it will have on future alarms. The parameters of the HAWK process are learned by optimizing a log likelihood function where the alarm sequences are the input data. So an example of the result can be seen to the right in the slide. This is an example involving 5 different alarm types. So the dots are the alarm events and the lines show how the intensity vary with time. So for example, in the figure, an alarm of type 3 or 4 at the bottom has a large probability of being followed by a type 1 alarm. So we can see that the intensity of alarm type 1 increases after each occurrence of an alarm of type 3 or 4. This information can then be converted into a causal graph. And in this graph, we keep all edges with a positive influence between alarms. So using the same example as before, alarm types 3 and 4 has a positive influence on alarm type 1. So these edges are kept in the graph. Then, after using HAWKS process, there are often some additional edges in the graph that are indirect or otherwise redundant. So to remove these edges, we use conditional independence tests. If 2 alarms that are connected with an edge in the causal graph are found to be independent, then this edge is removed. We tried 2 commonly used conditional independence tests, the Fisher-Z and the G-square test. The alarm transactions are used as input here, and as you can see in the figure to the upper right, the inputs to the 2 tests differ slightly due to their different nature. And an alternative approach is to add a regularization term to the HAWKS process loss function. But we choose to use the conditional independence tests here due to them being more interpretable. And our experimental results show that showed a more robust result using these. So as a final step, we want the end result to be a directed acyclic graph. And to enforce this condition, we iteratively remove the edge with the smallest intensity until this condition is fulfilled. So after pruning the causal graph, we want to encode some more information into it. We actually already have some edge weights in the graph given by the HAWKS process, but these weights do not account for any global effects on the causal intensities. So we propose to use a network embedding-based technique to infer more informative edge weights, and we call this method CPBE, or causal propagation-based embedding. Here we can see the 2 main steps of the method. So first we create an embedding for each node using the skip-gram model with our causal context generation process. The input to this process are the alarm transactions and the learned causal graph as shown in the picture. And then for each alarm transaction, we remove any nodes from the graph where the alarm is not present, as shown in gray. Then we traverse the graph starting from each remaining node to create a context. Here we can use any graph traversal techniques, for example, random walk or depth-first search. Then, following the skip-gram model, we train a small neural network to learn node embeddings using the generated context as the input. And in this way, we can obtain an embedding vector for each node. And now we simply set the weight between 2 nodes that are connected with an edge to be the cosine similarity of their respective embeddings. So Now we have created our alarm influence graph, and the next step is to deploy the graph and use it in the system to rank the alarms, and then make the root cause alarm predictions when a failure occurs. So let's take a closer look at how the influence ranking is done. The input to this stage is the previously created influence graph, as well as a single alarm transaction. And we again remove any nodes in the influence graph that are not in the alarm transaction and rank the alarms in each subgraph independently. And a simple example is shown in the figure where alarm F is not in the alarm transaction and is thus removed. And this splits the graph into two subgraphs that are considered separately. The actual ranking within each of these subgraphs is done by considering the problem as an influence maximization problem. And this problem is more well known in the area of social networks, where it has been extensively studied. And the aim is to select k seed nodes, which to turn, then will in turn influence their neighbors. And then any influenced neighbor will in turn influence their own neighbor, and so on. The goal is to select these initial seeds at k so that the expected number of influenced nodes is maximized. And there are actually numerous algorithms available to solve this influence maximization problem. And in our scenario, each subgraph is relatively small, and the actual algorithm is thus less important. So we directly select the influence ranking influence estimation algorithm, IRIE, for this task. So that's all about the framework itself. And now I will talk a bit about our experiments. So we evaluate our method on both synthetic and real-world data. For the synthetic dataset, we generate a random directed acyclic graph with a set average out degree d and with n different alarm types. And here we set d to be 1.5 to emulate our real-world dataset. Then for each edge in the graph, we sample a weight alpha from a range. Different ranges are tried here to see how different influences affect the result. We also sample a background intensity mu for each alarm type, and then we construct a multidimensional Hawkes process with both alpha and mu as the parameters to simulate event sequences. For the real-world dataset, we have about 1.5 months of data from a telecommunication network from a moderate-sized city in China. The total number of alarms of the preprocessing is a bit above 672,000, with 78 different alarm types from nearly 4,000 devices. And due to the difficulty in labeling causal relations, we do not have the ground truth causal relation for all the alarm types, but only for a subset of about 15 of them. And this translates into 44 known edges in the causal graph. Furthermore, to evaluate the accuracy in finding root cause alarms, experts have labeled 6,000 alarm transactions with the true root cause alarms. And the experiment is divided into two separate parts. With the first part, we try to assess the correctness of the learned causal graph. So here we use the 44 known edges as the labels. And here we have 4 different causal inference methods for sequential data as baselines. We have 2 methods using the PCE algorithm, one using the G-square as the conditional independence test, and one using Fisher's Z instead. We also have PCTS, which is an improved PCE algorithm variant for causal discovery in time series, as well as HPADM4, which uses multidimensional Hawkes process with a mix of L1 and nuclear norm. Here we have the result on the synthetic data and the real-world data. So the scores are all the F1 scores using the known causal edges. And our HPCI method outperformed the baselines for nearly all settings of N and alpha. However, HPADM4 obtains the best results with the very small n and small alpha. And this could be due to the distribution of the event occurrence intervals being sparse, which will make the causal dependencies straightforward to capture using a Hawkes process. However, when n increases or alpha increases, the events will be denser. Thus, Hawk's process have trouble distinguishing the instantaneous causal relations, and this is especially true when events co-occur. And we believe the use of the conditional independence tests helps HPCI by taking another perspective in which the causality is discovered based on the distribution changes in the aggregated data. If we look at the real-world data set instead, we can see that our HPCI algorithm outperformed the baselines in precision and the F1 score, while PCTS obtains the best recall. However, PCTS also has significantly lower precision, indicating that more false positive edges are found. And HPCI instead obtains a good balance between precision and recall in this case. So the second and the most important aspect that we evaluate is the actual identification of the root cause alarms. We use the causal graph obtained by HPCI and enhance it with the known ground truth causal edges to obtain as a good graph as possible. And again, we have 4 different baselines to compare with. We have IT, which uses the weighted causal graph as obtained by HPCI with the learned intensities as the edge weights. We have Pearson, which is an aligned Pearson correlation done on each alarm pair. We have CP, which sets the weights of an edge based on the number of times that 2 alarms occur in the same time window. And we have ST, which is similar to CP, but the weight is based on the number of times an alarm U occurs before alarm V in a time window. So here for evaluation, we use the 6,000 labeled alarm transactions with a known root cause alarm. And in the table here, we can see the accuracy using the different methods. The different Ks here are the different sizes of the seed set for the IRIE algorithm. So for K equals 1, we only consider the highest inference alarm, while for K equals 5, we consider the top 5 alarms. And as can be seen in the table, using our CPBE method to infer new edge weights, we have a significant improvement over the baselines with an accuracy of above 60% for K equals 1 and above 90% for K equals 4 or 5. So in conclusion, we propose an unsupervised framework for root cause alarm identification to help with fault management in telecommunication networks. And to this end, we introduced HPCI, a Hawk's process-based conditional independence test procedure for causal inference, as well as CPBE, a causal propagation-based embedding algorithm based on network embedding techniques and vector similarity for inferring edge weights in causality graphs. And our experiments show a significant improvement over our baseline models. Moreover, the solution is practical since it does not require any labels, and it's also fast enough to be used in practice with a running time of about 5 minutes on all the 6,000 alarm transactions that we evaluated on. So that's all for my presentation. Thank you for listening.